We are pleased today to welcome Yoann Altmann. So Yoann Altmann is a researcher at Heriot-Watt University. And so we are pleased to hear this talk today about expectation propagation for large-scale imaging inverse problem. Thank you, Yoann.
Thanks very much, Nelly, for the introduction. So thanks everyone for joining today. So I'd like to talk a little bit about the main principles behind expectation propagation for people who are not familiar with the method, and how we've been applying the method to large-scale inverse problems. I have to say, so this is joint work with a number of people and colleagues, including PhD students, former PhD students, and postdocs mentioned on that slide. I'd like to highlight the work of Dan Miao, who was the former PhD student, now a postdoc in the group, who's applied EP for image restoration problems. And so most of the applications I'm going to talk about today are part of her work. Okay, so let me see. Yeah, so I'll start with a brief motivation of the problem and why we need to use and develop variational inference methods before delving into EP itself, so expectation propagation, and I'll finish the seminar with a couple of applications from hyperspectral imaging to image restoration. So expectation propagation is an approximate Bayesian method, and so the keyword in there is Bayesian method. And so why do we need a Bayesian method, or in which cases do we need Bayesian methods? Mostly when we are interested in uncertainty management and uncertainty quantification. So not only we want to extract information from data, but also can we say anything about the remaining uncertainties about those parameters we are interested in? So all Bayesian methods have a series of key ingredients, which are depicted on this slide. So first we have data, right? So if we want to extract information, we need data. We may have side information or prior information about the problem or about the parameters we are interested in. And we also need an algorithm or algorithms to extract the information. And so this will depend, the type of algorithm that we will adopt will depend on the tasks that we are considering. So from a Bayesian point of view, the data is modeled with a conditional distribution, which is the first distribution on the left. It's the likelihood of the data, y. So y is the data, is what we observe, and x is the set of parameters we are interested in. So typically, in an image restoration problem, x is a noise-free image, effectively. So that's the likelihood part. Then we have the side information, or the prior information, which encodes everything that we might know about x before getting the data y. So that information can be either from expert knowledge about x, could be obtained from previously acquired data, or could be trained from a set of training data available. So now in the Bayesian context, once we have defined this likelihood function, so the forward model that links x to y, and once we have formalized this prior information through a prior model, we can derive the posterior distribution of x given y in here, which combines information from the data through the likelihood and information from the prior. So here we have a scaling factor which doesn't depend on X, so you can disregard that for now, but effectively we have the posterior distribution which is proportional to the product of the likelihood and the prior. And so that's everything we know about X. So before discussing the posterior distribution, I'd like to spend a bit of time discussing the likelihood and the prior in the context of this talk. So the likelihood will encode models that can be represented like this. So we have Y, the data related to X via a known linear operator A, plus some noise, because the world is not perfect. So the data we observe are corrupted by noise. So the noise is depicted as additive noise for now, but there could be multiplicative components within this random noise, like what we have when we have Poisson noise models, for instance. So that will be the likelihood for us today. Doesn't have to be Gaussian, could be something more exotic than Gaussian, IID Gaussian noise, but we have a linear model. Now, the prior could be either model-based, and by that I mean based on classical distributions like Laplace distribution, sparsity promoting distributions, Gaussian distributions, Gaussian mixtures, etc. Or they could be trained. If we had training data available, we could use the set of data to learn a prior and then use that as a proper prior or as an effective prior in our scheme. To simplify things, for now, we just focus on sparsity-based prior or model-based prior, which are proper distributions. Okay. So that's it. We have the likelihood, we have the prior. Note that the prior, although it's model-based, doesn't need to be log concave, doesn't need to be differentiable. Could be a mixture of distributions as well, like Gaussian mixture, Bernoulli Gaussian mixtures, these kind of things. We have a prior. Okay. Okay, so we have the likelihood, we have the prior distribution. What do we do next? The simplest estimator we can get, or we can compute from this posterior distribution, is usually the maximum a posteriori estimator, which maximizes the posterior distribution or the log posterior distribution. And this estimator can be computed or can be approximated very often using optimization techniques. So if we're lucky and the posterior distribution is log concave, we can use convex optimization tools and compute the map estimator very efficiently. The main limitation here is that well, we get a point estimate for X, which is already good, but we have limited uncertainty quantification tools beyond the I would say relatively simple log concave case. It's hard to estimate a posteriori, say, variances, covariances, or marginal variances. Especially when the posterior distribution is multimodal, when you have multiple peaks in the posterior distribution, we might find one of the modes, but so finding all the modes is hard, and estimating uncertainties is hard. So what do we do in this case? We can use sets of methods which are referred to as exact methods here, exact sampling method. Monte Carlo sampling. So the idea behind that is to use stochastic simulation to draw samples from the posterior distribution. And once we've done that, we can use the samples to estimate the map estimator, approximate the map estimator, the MMSE, compute covariance matrices, or approximate covariance matrices or marginal variances. So that's possible. But the methods usually struggle with high dimensional problems, especially when you start to have distributions that have multiple modes. Sampling and exploring the parameter space becomes quite challenging, and so those methods need to run for a very long time to make sure that that you explore properly the whole parameter space. So what can we do if we try and avoid sampling methods? We can use approximate methods, and those approximate methods will consider distributions which are not the exact posterior distribution, but relaxed versions of that. So in the sampling framework, we have methods, for instance, say your posterior distribution is not differentiable. How do you make it differentiable? Well, you smooth it, and then you use a Langevin-like diffusion algorithms to sample X. Okay, that's still sampling based. An alternative to that is to use variational inference, and in this case, the methods are mostly purely optimization based. So there's no or limited sampling involved in there, and those variational methods they all have the same goal, that is approximating the distribution of interest, so the target distribution here, the posterior distribution, by a distribution, an approximate distribution denoted by Q, such that Q is easier to manipulate than the posterior distribution, the true posterior distribution. And so among those methods, we have a variational base and all the variants of variational base. We have expectation-propagation, which I'm going to talk about next. And all those methods, they are based on using divergences to measure similarities between distributions. So what we want is we want Q to be close to F, but depending on the similarity measure we use, or the similarity metric we use, we will have different algorithms and we will have different approximations. So to unify a little bit that variational base, which is probably the most classical variational inference method and expectation propagation, I'd like to introduce first the family of alpha divergences. So if you're not familiar with those divergences, so you have the expression here at the top. So it's a divergence that measures the similarity between two distributions, say P and Q. And this divergence is characterized by one parameter, alpha, which can go from -infinity to infinity. And so you have an illustration at the bottom here that shows the impact of this parameter alpha. So if alpha is very large, say, we are on the right-hand side of the figure, we will have a fit. So Q is the approximating distribution, P is the target distribution, which has two modes in this case. We will have an approximation. So once we minimize this divergence, which will tend to cover all the regions where P has a non-zero probability. That means that it will cover very well this part here, but it's going to overshoot and overestimate the support of P in this case. On the other end of the spectrum, we have, so when alpha is very small, so the approximating distribution will tend to capture very well one of the modes of the distribution, but it might not capture very well the additional peaks. So in this case, you see that the estimated variance of the distribution, so the variance of Q is going to be smaller than the variance of P. In the other hand, the variance of Q will be larger than the variance of P. And so in between, we have the trade-off between, well, fitting one of the modes very well and covering the domain of definition of P. Okay. And so there are two remarkable values for alpha, which are relevant to the talk today. First one is when alpha goes to 0. So in this case, this alpha divergence converges to the KL divergence, the classical KL divergence between Q, so Q, the approximating distribution, and P. When alpha goes to 1, then the alpha divergence converges to another KL divergence, which is effectively the reverse KL divergence compared to VB. So it's a KL divergence, but it measures the similarity between P and Q. So if you're not familiar with the KL divergence, you have the expression just here. You see that this divergence is not symmetric, means that the divergence between P and Q is different from the divergence between Q and P. And here P is highlighted in blue just to show that this KL divergence, you can interpret at least the first part here, the first term, as an expectation with respect to P. So that means that P, the first argument of the KL divergence, is really a reference density when it comes to computing expectation. So that would be one of the main differences between VB and EP. So in VB, the reference distribution is going to be Q, the approximating distribution, whereas in EP, it's going to be, if not P, something close to P. That will be the reference distribution. Okay, so now a little bit about VB before delving into EP. So with VB, so variational base, the divergence we're trying to minimize is this one here. So we minimize with respect to Q, the approximating distribution, this divergence or this expectation. So that means that expectations are computed with respect to Q, which is quite convenient because if we choose Q to be simple enough, then we can compute expectations easily, so probably analytically. There are different versions of flavors of VB. The original one was mean-field VB, and the main assumption behind mean-field VB is that the approximating distribution Q is factorized as the product of its marginals. So this is what's reported here. So we don't impose additional constraints on Q, only that the approximating distribution is the product of its marginal. Now, more recently, there is another version of VB that's been proposed, mostly to train Bayesian networks, for instance, VAEs, where in addition to, or instead of using a mean-field approximation, we can constrain Q to belong to a parametric family of distributions, say Gaussian distributions. And in this case, because Q, say, is Gaussian, computing expectation with respect to Q is going to be simple. And in that regard, EP is a little bit like VB in the sense that we will force Q to belong to a predefined family of distributions. That's what we'll do. So that's VB with the original KL divergence, where Q is the reference density. Okay, how about the reverse divergence? If we use the reverse divergence, as I mentioned in the previous slide, now expectations are computed with respect to the target posterior distribution. Well, that's not very practical because if we were able to compute expectations with respect to the posterior distribution, then, well, we wouldn't need variational inference, right? Because, well, if I knew how to compute the mean of X or the covariance of X according to this distribution, then the problem would be solved, or at least in 99% of the problems would be solved, because what we primarily need from X is the mean and the covariance or the marginal variances. So minimizing this cost function here, well, is very hard. I don't know how to do that. We don't know how to do that. So what do we do instead? Well, before answering that, I'd like to mention, the case where Q is Gaussian. So let's go back to this, and let's assume that Q is Gaussian, because that's going to be useful later on. So if Q is Gaussian and we try to minimize this KL divergence, the solution that we get is that Q is a Gaussian such that the mean of Q is the mean of the posterior distribution, and the covariance of Q is the covariance of the posterior distribution. And so this is what's called moment matching. So when we try to minimize a KL divergence that looks like this, the solution is given, assuming that there's no additional constraints on Q. Q is just Gaussian. The solution is given by those two equations. So we match the mean and we match the covariance of the two distributions. So as I said, we won't be able to do that directly with the posterior distribution, the target distribution. But in practice, what EP will do, it will minimize a sequence of KL divergences where this distribution here will change. P tilde is going to change, but at each iteration, we will try and have P tilde close enough to the posterior distribution. And so that's how EP is going to run. Okay, so now let's go a bit deeper into the implementation of EP. Still with the same factorization of the posterior distribution I mentioned before. So we have a posterior distribution which factorizes up to a scaling factor as the likelihood times the prior. With EP, we'll adopt a similar factorization for the approximate distribution. So we will construct Q, the approximating distribution, as a product of two distributions. 90% or 95% of the time, those will be Gaussians. So we'll have Q1 that will mimic the likelihood, which is usually not Gaussian, and Q0, which will mimic the prior distribution. So we're not going to directly estimate Q. We will estimate two distributions, Q1 and Q0, and we'll do that sequentially. So how do we do that? So we have the two minimization problems that will be solved within EP. If we look at the previous equation, so we had the true posterior here and the approximating distribution over there. What we'll do with EP is the first step, we will keep the true prior, which is this one here, and instead of taking the likelihood, we will replace that likelihood by its approximation, Q1. And hopefully, this distribution here, which will be called a tilted distribution, will be easier to handle than the original posterior. So we have this KL divergence. We optimize it with respect to the other factor in our factorization. So that's Q0. And that's our new update for Q0. Once we've done that, we swap the terms. So we keep the true likelihood, and we replace the prior by its approximation, its Gaussian approximation. So again, this is going to simplify, hopefully, the computation of expectations, and we can update Q1. And once we've done that, we iterate. So we will update Q0 again, Q1, Q0, Q1, until the algorithm converges. So the key step in the update will be really to compute the moments of these tilted distributions. So as I was saying before, so you have a Gaussian on the right-hand side, second argument of the KL. And if you want to, the KL divergence, so if you want to minimize this, you'd like to match the mean and variance or covariance of the distribution on the left-hand side and right-hand side. So hopefully that's going to be manageable. It's still hard in high dimension because, well, first we have high dimensional integrals to compute, but we have to manipulate and we have to estimate large covariance matrices or large precision matrices. And that can be tricky if those covariance matrices are not structured. So what's typically done within EP is we add additional constraints on the covariance matrices of Q1, Q0 to simplify the two minimization problems over there. So a point I will come back to later on is that by doing so, there will always be a trade-off between the complexity of the algorithm. So how expensive are these two minimization problems versus how accurate the approximation is. Okay, but I'll come back to that later. Okay, so one of the main, I think, fascinating aspect of EP is that it has multiple interpretations. So one is, as I said before, an iterative algorithm that minimizes KL divergences at each iteration. But you can also look at that as a message passing algorithm. And here I'm showing a factor graph associated with so the Bayesian model and how we can run message passing with EP. So if we look at the first line here, which is the first step of EP, what are we doing? So we're using a Q1 as a proxy for the likelihood, and we use that to update Q0, the approximate prior. So we can look at that as having Q1 being a message being sent from the factor node on the left-hand side towards the block on the right-hand side. And so Q1 is a message sent to the prior node to update Q0. And in the same way, when we look at the second update, so the second update is using what? It's using the approximate prior, so Q0, which can be seen as a message that's sent to the likelihood factor to update Q1. And so these are messages going back and forth between the two nodes of this factor graph. Okay. And so from an implementation point of view, this makes EP very modular because if we want to change the prior, the only thing we need to change is the update of this block here. So we don't change really what's happening here because irrespective of the prior, the message that's going to be sent to the likelihood is this Gaussian approximation, and then the other way around for the likelihood. So if I want to change the likelihood, provided that I can still compute moments there, I'm just changing the update of one block. It's a little bit like using ADMM or using splitting methods with different priors or different likelihoods. Changing the prior only changes one of the updates, one of the blocks. Now, it might be that with this simple factorization that's here, some of the updates are not tractable because analytically we cannot compute the mean and variances of those tilted distributions. So what can we do in this case? One option is to use Monte Carlo sampling to sample from the tilted distributions. So those tilted distributions are simpler than the original posterior, so maybe they are easier to sample. But still, if we do that, we lose a little bit the benefits of EP in the sense that we would like to use optimization as much as possible and not use sampling. Another option is to say, okay, I'm going to split one block, which is difficult, into multiple smaller blocks. So that is equivalent to extending the Bayesian model, and I'll run EP or message passing on this extended model. And this is something that illustrated on that slide. So imagine that you have a Gaussian, non-Gaussian likelihood, so say Poisson likelihood. So what you can do is split the likelihood block into two blocks. You introduce an auxiliary variable there, and then you decouple the noise statistics, so the Poisson statistics, from the linear operator, exactly as you would do with ADMM, for instance. So you get a new factor graph, new update rules, but the message passing mechanisms remain the same. So you have three updates here. One, that's taking information on messages from the central node, sending that to the node on the, or sending that to the factor on the left-hand side. The second update is taking information from both extremes, messages that are sent to the central node to update Q1 of U and Q1 of X. And then you have another update that's passing messages from the central node to the node on the right-hand side. So the mechanisms remain exactly the same. Okay, so now I'll move on to a few applications where these principles can be applied, starting with a spectral mixing example. So if you're not familiar with hyperspectral images, so these are generalizations of the standard RGB images, but instead of having just three channels RGB, you can have hundreds or thousands of spectral bands. And this increased spectral resolution allows you to discriminate objects that by the naked eye would look the same. Okay. So here you have an example in this figure where if you look at individual pixels, okay, so you look at them through the different wavelengths, you can extract a spectrum. And the spectrum of that pixel is going to be dependent on the content of the pixel in terms of which materials are present in the pixel. So if you have a pure pixel that only contains water, you'll have a characteristic spectrum. If you have a pixel purely composed of one vegetation species, you'll have also one spectral signature. If it's pure soil or pure rock, you'll have also characteristic signatures. The unmixing problem arises because of the limited spatial resolution of those images. So what might happen is that in some pixels, you'll have more than one component. And so what you observe in practice is a linear combination of the pure spectral signatures of those pure components or end members. And so that is something that you can formalize with this forward model. So you can stack all the spectral signatures of the pure materials in this matrix A, and the unmixing problem consists of estimating the proportions or the abundances of those materials. So why did we want to use EP for this problem? Well, we wanted to investigate sparse linear regression problems, where because we don't expect to have lots of material within each pixel. So we wanted to try and estimate X, assuming that it's sparse. So in each pixel, so you have a vector X, which is expected to be sparse. And so because EP doesn't rely on a differentiability of the prior or the fact that the prior has to be unimodal, that was a good candidate application. So we applied EP to that. The algorithm is very similar to the one I discussed before, but instead of splitting the likelihood, we can split the prior. Okay. So we can obtain results like this in this figure. So the first thing to look at here is the top row. So the top row, you have the abundance maps. So associated with the 5 components assumed to be present in the scene. And so those maps tell you where the 5 components are likely to be present. So in here for the first one. The second one is relatively spread. This one is quite concentrated at the bottom, and so on and so forth. So that's okay, but that's just a point estimate. One of the benefits of the Bayesian method and EP in particular here is that it also gives you approximate marginal variances. And so this is what we have at the bottom here. So those maps are interesting in the sense that we see that the marginal variances change across the pixels, and they depend on the actual composition of the pixels. Because so finding or estimating the proportion of materials in mixed pixels is more challenging than identifying proportions of almost pure pixels. So this is the type of information that can help us identify or quantify the uncertainties around those abundance maps. Something that I haven't mentioned in detail is that, well, as a byproduct of the algorithm and the way this prior has been splitted, EP can also give us marginal probabilities of presence for each component. So it's not doing a hard classification saying this pixel is mostly composed of that material or that one or that one. We can decide whether, or we can estimate how likely it is that each component is actually present in each pixel. And so this is what we have in the middle row over here. Now, this is high dimensional in the sense that we have lots of pixels, but because of the decoupling of the prior distribution, all the computation is almost done at the pixel level here. So this is not really a high dimensional problem. The problem becomes more challenging for implementing EP when we consider image restoration problems. So still we have the same forward model. So Y is a distorted version of X, the image of interest. And now A can represent, well, if it's the identity, it's just a denoising problem, could be a blur operator, could be a binary mask for in painting, for instance, in painting problems. And now X is really an image. So that could be millions of pixels. The problem when we try to apply EP here is that we very quickly have to manipulate very large matrices, operators like A transpose A or A transpose, and that makes the implementation of EP challenging. So, as I said before, we can use Monte Carlo sampling for some of the tilted distributions, but still we have to be very careful in the way we design the splitting to make sure that the algorithm can be scalable and can be applied to large images. So in the context of image restoration, something we weren't really interested in is trying to understand the impact of the prior distribution. And as I said before, so EP is quite modular. So if you just want to change the prior, you change a block, and you only need to create the updates for that block, but the rest remains the same. So one of the things we looked at in the context of denoising is the shape of the prior. So in this example here, we looked into priors that are promoting sparsity of the gradient. So typically, the classical prior, the total variation prior, is based on the L1 norm of the gradient, which is equivalent to assigning a Laplace prior to the gradient. But we can have more aggressive priors that, for instance, put an L0 type of penalty on the gradients. So we can have like a Bernoulli Gaussian or Gaussian mixture prior assigned to the gradients of the image. And so these are some of the results we've obtained. I would like to focus more on the two columns on the right here. So the far right column is the results obtained with total variation with an L1 prior. And this one is with a Bernoulli-Gaussian prior. And again, because EP doesn't really care about the differentiability of the prior or the likelihood, we can apply it regardless in both cases. So in terms of PSNR, for this type of images, which are very cartoonish images, well, this Bernoulli-Gaussian prior makes a lot of sense for as a prior for the gradients. And what we've seen is that the PSNR is better than when using the L1 prior, but that really depends on the texture that's present in the images. So there might be images where the L1 prior is better results. But what's interesting is that really we can use EP to understand a little bit what the prior is doing in the posterior variances. What we see here, when we compare those two images, which are the marginal variances, we see that well, both priors can identify that the regions of high uncertainty are the edges of the image, whereas regions that are quite homogeneous have low uncertainties, which kind of makes sense, right? The gradient is 0 or close to 0, so we can use local averaging to estimate the intensities. Now, the interesting difference is because of the L1 prior, that doesn't make the difference between homogeneous regions and edges. The high uncertainty regions have lower uncertainties compared to EP, compared to the other prior, sorry. Whereas the homogeneous regions have higher uncertainties compared to the other prior. So this is the kind of tools that can be useful for image analysis and quantitative analysis of the results. Now, those results have to be nuanced a little bit, because what I'm saying is the PSNR is better with this prior than this one, but that depends on how we tune, how we select the hyperparameters or the parameters of those priors. So in everything I've talked about so far, the prior was assumed to be perfectly known, but in practice, especially for regularization purposes, we don't really know how much we should regularize the image. So we can do that with EP by just extending X. So we create a new vector, we put everything in there, X and the hyperparameters, and we run EP with that. Usually, it's a bit more complicated to compute the updates, and it doesn't give us the best results because we are effectively marginalizing a theta when we estimate X. Something that works better in practice is to run some kind of EM algorithm, so expectation maximization algorithm, where we estimate theta by a marginal maximum likelihood estimation or marginal map estimation. So conceptually, running an EM on this type of problem is fine, but in practice we can't, because in the E step of the EM algorithm, we need to compute expectations that are not tractable. We can do exactly the same thing we would do with a variational base within EM, so variational EM. We can do the same with EP. So we just replace the untractable distribution by the one estimated by EP, and that gives us an EP-EM algorithm. And so we can use that again to estimate theta for each image. So we've applied that to a series of problems, like well, tuning or adapting the prior, and also in the case of blind deconvolution, if you want to estimate the blur kernel, so you can use exactly the same thing. So it's not the prior that's not well characterized, it's the likelihood. So the likelihood depends on some kernel parameters that you want to estimate. So I'm going to show you one a result associated with so deblurring problem, non-blind. So we know the blur kernel, but we just want to tune the prior. So we run EPEM and we estimate theta as well as the image. And once we have that theta, we can compare the estimated images obtained by running either an MCMC algorithm, which will target the correct posterior distribution, or VB. And so at the top here, you have the estimated images for the three methods. So visually, they are very similar. VB can be a bit better because it approximates, well, the approximate MMSE estimator from VB is closer to the map than it is from the MMSE estimator. So in this case, it's slightly better. The interesting bits are the uncertainties, the estimated uncertainties. So the reassuring part is that EP gives uncertainties that are in line with the gold standard, so with the true uncertainties. They are not exactly the same, but they are close enough. And what we see with VB is that it dramatically underestimates the uncertainties. So that doesn't mean that VB is better because it gives lower uncertainties. What it means here is that VB is overconfident and it's underestimating the uncertainties. So I'm going to skip those results, which are about blind deconvolution. And I'll conclude my talk just here. So I've discussed some of the benefits of EP in the sense that it can be a cheaper way or a cheap way to approximate means and marginal variances, cheaper than Monte Carlo sampling. And something that we've seen in practice is that when it converges relatively quickly. So much quicker than, say, ADMM for map estimation. But it's not the ultimate tool for sure, because in most of the cases, there's no convergence guarantees for IP. So we cannot ensure that it's going to converge. So there are strategies or mechanisms in place to help EP converge, such as damping, for instance. But even when we damp, sometimes EP doesn't converge. And when it does, well, that's something that clearly we can see. When it doesn't converge, it's usually because the assumptions that we've used are not appropriate. So I said before, the quality of the algorithm or the results is as good as the quality of the approximation. So if we assume that the distribution is Gaussian and the posterior distribution is really not Gaussian, so EP might collapse. The same way, if we use a mean field approximation and that approximation is not relevant, so that's when EP might fail. And so that opens routes for improving EP in high dimension by looking into more complex structures for the covariance matrices. For instance, using block diagonal covariance matrices, which can be combined if you multiply two Gaussians with structured covariance matrices. Those block diagonal structures remain. The same when you have low or quasi-low rank structures. If you multiply the two Gaussian densities, you still have this low rank structure that appears. And so I'm going to conclude with that. In the prior models that I used today, so those priors were model-based. But what we've seen for image restoration is that now, especially with map estimation, we can get much better results by using trained priors. And so given the strong links between ADMM and EP, something that's interesting to look at is, so could we have an equivalent of PNP ADMM with EP, some kind of PNP EP? That's challenging because we are not only interested in point estimates, but also uncertainties. And so when we have priors that are trained or that are modeled by neural networks, So the covariance structures become very difficult to handle. So there's still a bit of work to be done there. However, we can try to use EP to approximate those trained priors, for instance. And so I'm mentioning here variation-oriented encoders and spiking neural networks. So that's ongoing work where we're trying to train effectively such networks with EP. So that's pretty much all what I wanted to discuss today. So thanks very much for your attention. And yeah, if you have any questions, feel free to use the chat or I don't know if we can use the mic, but yeah. Thanks very much.
Thank you very much, Yoann. So is there any questions? So yes, I'm going to take one. Okay, I think I can. So Barbara would like to ask a question. We will try to make it work. Barbara, can you try to speak?
Hi, can you hear me? Yeah, perfect. So thank you very much for the presentation. I wondered in this framework, how to estimate the error on the estimated variance. If, for example, I have a map estimate, I use optimization, I can easily choose a ground truth, X, then apply the forward model, add some noise, potentially some blur. Then I have some observations, and I can compute the difference between the estimate and ground truth, and for example, square norm, and then I have a measure of the point estimate error. But when I want to estimate the error on the variance, what can I do?
So, well, the way we've done that in the past is by comparing the variance or the covariance matrix to the true covariance matrix of the posterior. So for that would be comparing with the MCMC covariance matrix, assuming that this one is reliable.
But it was never done, for example, to choose a fully Gaussian model for which we know exactly the covariance in order to see whether it can be recovered?
Sorry, can you say that again?
If I imagine a simple Gaussian model for which I know the covariance, can I generate synthetic data and check that I have the correct covariance? And is it interesting to do that or too simple for more general conclusions?
So if you know if you know exactly the posterior covariance matrix, then you can use that instead of Monte Carlo sampling. Yeah, indeed. And so then you compare the estimated covariance matrices still in the same way.
And to your opinion, is it interesting to give some hints of the ability of MCMC or EP to estimate to sample under intricate posteriors, or is it a too simplistic toy example on which there is no information to extract?
So what you can use, well, if you don't have access to if you have access to the true posterior distribution, that will probably be toy examples or simple examples. In this case, yeah, that's fine. In the more complicated cases, we don't really know. We don't really know the so we don't know the covariance matrix. What we can do is we can use multiple, let's say, EP models with different approximations and compute the KL divergence after. So what is it? You can compute the KL divergence after convergence and do some kind of model selection based on that. So to check which of your EP approximation is the best. Does that make sense?
Yes, yes. Thank you very much.
Okay, thank you. Is there any other question? You can raise the hand as Barbara did if you are interested. Okay, maybe I can ask a question. So it's a bit in the same spirit that the question of Barbara. You said to us that this algorithm, so you showed that it works well, but you have no convergence guarantees. The point is that I guess that for solving some kind of the problem you presented, you can have algorithm with convergence guarantees, and one thing could be to compare with this algorithm in order to see what kind of interval you obtain or quantification you obtain with this algorithm, and then compare the one you obtain with your method. Have you done it? Is there any way to do that quite simply? Or?
Yeah, so that's what we try to do when, so say we were looking at, yeah, I'll say this problem there. Well, yeah, this one there. So in this case, so it's a deblurring problem, Gaussian noise, TV prior, so the posterior is log concave. And so in that case, we can trust the MCMC algorithm as being targeting the right distribution and being able to converge, etc. So that's why it is a toy example in the sense that the prior is simple, but it's simple enough so that we can apply the MCMC algorithm and we can trust that as reference. Yeah.
Okay, thank you. And I also have two questions, maybe in order to give some intuition. The first one is about the slide 5. So you say you had two items. One was sampling with an adjusted Langevin diffusion, and then optimization based. And my question was, in a sense, can't we consider that an adjusted Langevin is also based on optimization scheme in a sense? And I'm not sure to understand why you have this this distinction between both. So
Okay. So what I mean by that is so we can either sample and get samples from a distribution which is either the exact one or an approximate one, but that's still sampling based. So we need to have lots of samples to be able to get an approximation of the say posterior mean or posterior variances, which is a Monte Carlo estimate. Whereas with the variational approach, what I mean by optimization-based variational approach is you get that estimator by optimization without sampling.
okay.
You see what I mean?
Yeah, but actually in both you have optimization scheme.
Yeah. And that's something fascinating when we start to mix the methods. So you can have either optimization within sampling, which is kind of what the Langevin diffusion is doing, or the other way around. So you have an overall scheme which is optimization based, and within that you have stochastic approximations.
Okay.
Yeah.
Thank you. And I think the other comment was in slide 9.
Yeah.
Yeah, I think, okay, could you give me some intuition about the way that you should select Q0 and Q1? Because it seems that there are some, I don't know, some rules to follow, because depending on the choice of F, and you will have more adapted Q1 or Q0. Could you just comment a bit on that?
Okay. So the main criterion will be whether X should be considered as a continuous or discrete. So if it's continuous, the Gaussian approximation makes sense. Makes sense. makes our life easier, because when you multiply two Gaussian densities, that remain Gaussians. And that wouldn't be the case with, most of the other multivariate distributions, continuous ones. So that's why it's easy for us to say to use a Gaussian approximation. If it's discrete, we can use like categorical distributions. It's more adapted. The main thing is to make sure that whatever we choose here, we have updates there that are tractable or that are relatively simple. And for multivariate distributions and continuous random variables or random vectors, I would say, it has to be Gaussian. Otherwise, it's very quickly not tractable.
Okay. Thank you. We have a comment by Nadir Mustafa. Maybe I can ask, so it's in the chat. He asked, is the method of EP have any real application in case of image transmitter? If yes, how the algorithm works and how can minimize the image losses after the model convergence?
Okay. Thanks very much for the question. I'm not sure I'm understanding what you mean by image transmitter.
I can maybe, Nadir Mustafa, I can allow you to speak if you want. I'm going to allow you to speak and you will see.
Perfect.
Hello, Nadir? Okay, I don't know. Hello, Nadir. Could you specify your question, please? Okay. We have no.
Yeah, Nadia, we can take that question offline. So sorry. So the slides will be shared. My email address is over here. So if you have any questions, just feel free to drop me an email.
Great. So thank you very much, Yoann, and okay, see you in the next webinar.
Great, thanks very much. Thanks for the invitation. Thanks very much, everyone, for attending.
Bye.
Talk to you soon. Bye.